The Marine Tech Expo is going virtual this year. Welcome back to the 2021 Marine Tech Expo. Coming up in this session, we'll be taking a closer look at the application of marine technology in the defence sector, including communications in the underwater battlespace, the development of unmanned underwater vehicles, and mine countermeasures. But in the first part of this session, we'll be looking at the use of digital twins as an enabler for condition-based maintenance in unmanned platforms. Leading us through this is Robert Allen, Chief Engineer and Digital Twin Lead for Babcock Defence Systems Technology.
My name's Rob Allen. I'm a Chief Engineer here at Babcock International, and the topic of my presentation today is using digital twins as an enabler for condition-based maintenance in unmanned platforms. I always start with this slide when we do presentations. It's not because we don't think people understand what digital twins are, but because we often joke that if you ask 100 different organisations what a digital twin is, you'll get 100 different answers. So for us, when we're talking about digital twins, we're really talking about taking in-service pieces of equipment and then we're retrofitting them to become very intelligent pieces of hardware. So think systems that can order their own spare parts, systems that can request their own maintenance, systems that understand the condition of their internal systems and can report back to us on it. And that gives us a real important advantage for helping our customers. And that is being able to predict how something is going to perform and when we need to take maintenance, and obviously switch over to a sort of condition-based maintenance approach. So our dream for a digital twin system, and what the goal we're always striving towards, is for our system to pick up a problem with an asset if one occurs, but before any kind of reduction in performance has occurred, any kind of issues has cropped up. That then gets fed back to us, and we can make sure that the next time the ship or whatever asset it happens to be pulls up alongside, one of our teams there ready with all the right parts, all the right tools, everything they need to do the job, so they can jump in, make that repair, and leave the customer to it without them ever really understanding that there was a problem or ever needing to know or do anything differently. So that's really what we're looking for. And the asset you can see in the slides there is the 4.5-inch Mark 8 naval gun. And that's really been our sort of proof of concept. It's our first of class system that we're looking at. It's a really good candidate for this kind of technology because it's sort of a 1970s vintage piece of equipment. It's incredibly powerful. It's really, really accurate. It's absolutely awesome, but it is 1970s. I think it was upgraded in the sort of 90s. So it's that kind of vintage technology. And we're sort of taking that and bringing it up to being one of the sort of smartest weapon systems you can imagine. To enable our digital twins, we kind of had to come up with a fairly new architecture. So I think it's fair to say that if you look across industry, other sort of competitors, if you call them competitors, but most people sort of see things like 5G as a key enabler for digital twins because they're looking at sort of taking information that a system already collects. If you take a car, for example, there's a whole bunch of sensors fitted to the vehicle. That sort of information is captured and then it's sort of bulk transferred back via something like 5G. And it'll probably go into sort of a cloud solution, a very high performance PC in the cloud somewhere that will do some very clever maths, and it will use that to understand the condition event. And that is great. It's a really, really good system, but we've got some unique challenges in defence that really make that not achievable for us. So where we started with this is actually right at the very beginning with the asset itself. So we've produced some enhanced telemetry, which is a system we call the data acquisition unit, or adapter is another name for it. That's effectively a data acquisition system that goes actually on board. It becomes embodied as part of the asset. That enables us to capture large amounts of data from all sorts of bits and pieces that are happening inside the gun, but things that wouldn't normally be captured as part of its running. So things that enable us to make better decisions about it. We can do all of that with this unit. But where it differs again is that we've had to equip it with a really, really powerful edge processor. So all of our processing is done actually on board at the point it's collected, and we can just then trickle back sort of very, very tiny amounts of data. And we anticipate when these types of assets in service, we might get dial-up modem connection speed, and maybe we'll get it for an hour a day, maybe an hour a week, maybe an hour a month. So our system has to be able to work completely autonomously by itself, and we just want to be able to update it when things happen, and we want to be able to learn from it, but just from those sort of very, very tiny breadcrumbs of data. So from there, obviously, we do need a way of getting the data back, even though we anticipate it's going to be quite a slow way of getting the data back. So we're building our systems to be really flexible to work with things like the Army's Project Thea or the Navy's Project Nelson. So a very flexible communications protocol. Then we've got sort of the key part of our approach, which is a combination of black box and white box modeling. So if you're not familiar, black box modeling is your kind of machine learning, artificial intelligence type of techniques. And they can be really good, targeted in some areas, but really the best possible performance is through white box modeling, which is what your sort of traditional engineering modeling would do. We'll talk about that on the next slide, but really that's a really, really good way that we add value as a business, because we understand these assets so well. We can produce these really accurate, really high performing white box models. They are quite expensive and they are quite time consuming, and really through this piece of work we really understood why everyone is excited about digital twins, but also why not many people do them, because they're incredibly difficult. So from there, we've got the virtualized input you can see. So that is effectively extending the virtual environment to include real hardware. So we really want to be able to test design changes, do all the kind of things that we would need to do to sort of really, really make an asset as robust as possible, and do as much as we can in that sort of virtual environment before we actually start looking at real hardware. So we were talking about the 4.5-inch gun on the previous slide. If you take that, for example, if we want to do an update to that, we might want to put it through 1,000, 10,000, 100,000 virtual rounds, really, really put that update through its paces before we actually put it anywhere near a real gun, sort of help with performance. Then the last thing we're looking at is sort of new ways of visualization, which we're looking at sort of VR and immersive environments to look at data differently. So what we've learned so far in doing this is that digital twins are incredibly powerful, and white box modeling is incredibly good, but it's also quite expensive and it's quite time consuming. So we've condensed everything we've learned into this sort of spiral diagram, which you can see in front of you. What we're saying is here is, I appreciate it's quite a complicated diagram to follow, but you really, all projects start kind of the same way. So we take an existing asset, we sort of collate all the data that's available to us, we identify where likely root causes of failure, things we need to understand, we develop a sensor strategy, we install the data acquisition system that I spoke about on the previous slide, then we collect some data, and we really start off with that manual sort of white box modeling, and we go around that loop, create the model, remotely download it onto the data acquisition system, put it into service, learn from the data we get back from it, and we go round and round that loop until we get to the right sort of performance that we want, where everyone's happy with what the asset's doing and we've achieved our goals. That means we're not sort of white box modeling things unnecessarily, we're not sort of spending money unnecessarily. It's the quickest way to sort of deliver early benefits and get to a digital twin in the most sort of efficient way possible. So that's our sort of previous work on digital twins. The actual, obviously, this talk is about condition-based maintenance in unmanned vehicles. And so for that, we'll jump to the next slide, and you'll see a Cummins 6BT engine on there. That's a bit of a stalwart. It's a sort of tri-service engine, really, really, really good, really robust, really reliable engine. But obviously, eventually everything fails. And one of the things that we're understanding quite quickly when we're starting to look at this is that people are actually really, really good at understanding anomalies and reporting back on anomalies. So where we're looking at sort of 40% of the failures of this engine, roughly 40% are linked to loss of compression. Actually, those failures are not falling into the most expensive cost bracket. And they're not always falling into the most expensive cost bracket because they very rarely run to failure. And that's because the drivers are really, really good at picking out very subtle clues and using that to predict when the engines are going to go wrong. So we get feedback. If you look at the condition reports, it'll be things like, oh, there was a weird smell came into the cabin when I was, doing XYZ, or it made a really weird noise when I went around this corner, or something didn't feel right when it started. It's those kinds of really subtle things that humans are really good at picking up. So if we take a system like an army vehicle that this is from, and we look at making that unmanned, straight away you're going to have worse performance straight off the bat. Just because of that, you're taking that human out of the loop, and you've lost that really, really clever anomaly detector that sits in the driver's seat. So this project really is about, can we use a digital twin to start to bring back some of that intuitive nature that a person will bring to the table here, and start to try and bring that condition-based picture in, and hopefully sort of bridge that sort of gap. So for this particular project, we're looking for a system that can remotely detect and monitor and diagnose subtle changes in engine compression, which is that sort of really big 40% number that we're targeting. Also looking at failures in the fuel system. Now it's a much smaller problem, sort of about 5% of failures, but actually those two could be intrinsically linked. So they're really important that we look at them together. So to do that, this is what we sort of come up with. So what we're doing here is very, very similar to what we've done in some of the 4.5-inch gun stuff, which is compression gives us a really difficult problem because it's not something you can just directly measure while it's in service. So we need to be able to understand what the sort of compression levels of those cylinders are, monitor it, predict it over the long term to be able to take action. But we can't do that directly. So we fit sensors around it where we can. We use a physics model to fill in the gaps on those sensors. So we've got things on like the injection pump, the intake manifold, things where it's relatively easy. Easy is probably not the right word, but it's doable to add sensors. Then we develop a one-dimensional model. We use that to predict the health of each one of those cylinders individually in real time while the engine's running. So that's quite an exciting thing. It's quite an exciting prospect. We've actually released a research paper on this recently, which NATO have published. And we've partnered up with Surrey University to actually create that one-dimensional model. So I think there's some fair to say they're kind of one of the world leaders in creating those kind of models. So we partnered up with them. Our plan is to sort of fit out about 10 to 15 vehicles initially with that system. Capture as much data as we can and use that model to predict the compression and the health of the fuel system remotely, which, as I said, we'll then use to try and work out whether we can bridge that gap. Where we are with the project at the moment, the Army have very, very kindly lent us a power pack from one of their vehicles. We've stripped that down, which you can see in the photos. We've added the sensors that we talked about on the previous slide, and we've taken it up to Surrey University and installed it on the dyno. So if you're following the sort of spiral diagram we spoke about a few slides ago, the next step is to collect some live data. So we're just starting to do that now. We've collected a few hours of running data. We've already managed to diagnose a problem with the engine, which is a faulty fuel injector, and fix that before we had any problems. So initially, very, very positive outlook on it. So we're going to collect some more data. We're going to produce that one-dimensional model probably in the next sort of 3 to 5 weeks, somewhere in that sort of range. At that point, we'll then be looking at fitting out, as I said, those sort of 12 in-service vehicles. And then from there, we will look at analysing that data and probably producing a follow-up paper on how that's gone and whether it's something that we could potentially use in the future to sort of bridge that human gap. So that's everything from me. Thank you very much for listening to the presentation, and I'll leave it there.
Our thanks to Robert Allen from Babcock. And a reminder, if you have any questions, you can submit them on the comments section of the YouTube channel. Next up, how marine technology is being used in maritime mine countermeasures. To explain more, here's David O'Sullivan from Thales.
Hi everyone, I'm David O'Sullivan and I'm the Maritime Autonomy Capture Lead for Thales UK. And to start with, I just want to say it's a great pleasure to be speaking at the Marine Tech Expo. It's also really encouraging to see such a wide and diverse set of speakers from across the maritime domain. For me, this is my first presentation of Thales capability in this area, as I've only recently started in this role at the beginning of June. However, for me, Plymouth is where I started my career in maritime. It's a bit of a homecoming for me. So I joined my first submarine back in 1990, which was the Devonport-based HMS Trafalgar, and I spent the early part of my naval career based in the southwest. Unfortunately, the naval drafter had different ideas and sent me to the not so sunny climate of Faslane after our first 3 to 4 years in the southwest. I stayed in the Royal Navy for 14 years in the submarine service and have worked in the engineering teams in Thales UK, focused in the underwater system business. That's primarily because of where technology's been. It's been on traditional platform types, and that's been across all the various maritime areas, specifically submarine, surface ship, and mine countermeasure platforms. I've covered both the domestic market and some of the export programs as well, so I've had a wide exposure of different capabilities and different customer types. My most recent roles have been in the support area of the business, which has also added some wider knowledge and skills to my portfolio. And these, I'm certain, will help in understanding the wider challenges associated with the introduction of emerging technologies. During my time at Thales, I've also seen the evolution from closed and bespoke systems to open architectures, enabling agility and capability insertion. From this experience, I'm aware of the wider challenges associated with agility when applied in complex systems. I'm just going to move on to the next slide now, which talks a little bit about why Thales chose Plymouth. So for Thales, Plymouth and the Southwest has significant strategic value from its growing marine technology ecosystem, its significant maritime-focused educational services, and the social values that Plymouth City Council is embracing, all of which will help support growth in the maritime sector. Turnchapel Wharf was originally established to support the Maritime Mine Countermeasures Programme, also known as MMCM, but we also considered the need for wider autonomous focus, particularly within the ASW domain. Additionally, coastline diversity was a key factor, and it provides the ideal trials ground for Thales's autonomous vision. The MMCM programme, which is due to deliver the first fully operational units to both the RN and the French Marine Nationale in 2022, is on the back of successfully completing a significant trial programme managed and based out at Turnchapel Wharf. With MMCM, the autonomous element has rapidly matured technology readiness levels, and although the mine countermeasure autonomy continues to develop at pace, our focus is widening across the naval and civil autonomous programmes, studies and trials. In Turnchapel itself, we have future developments plans for the site, which includes an autonomous operations centre. We are looking at the next generation of unmanned surface vehicles, wider trials and demo assets, supporting the 5G comms network as part of Smart Sound, and also looking at the security elements of a compound moving into wider naval domains. If we move on to the next slide, we look at how we're going to grow revenue. So although the initial MMCM trials are complete, the programme is actually gathering pace as we continue to qualify and also train the Royal Navy's Maritime Autonomous Systems Trials Team, and they're better known as MAST. The benefits of the Plymouth-based trials capability in MMCM and wider autonomy is key to future growth, and we'll be conducting further trials with MAST as the MMCM programme progresses and delivers its next set of deliverables. Additionally, later this summer, wider research and development testing will be conducted to accelerate the technology readiness level of some key ASW capability. On the next slide, we're going to discuss what does the future hold. So for us, a key enabler is establishing a brand architecture for the facility. This will include an immersive design centre, allowing clients to learn more about conducting trials in a safe space. It will enable the creation of the right trials to achieve the evaluation objectives and optimising a trials package. Through these simulation, you can design the path to trial success and also certification. The Autonomous Operations Centre moves away from traditional trials to actually supporting full autonomous operations. And additionally, within Thales UK, we have now established an Autonomy Technology Centre, which enables us to maintain an agile and evolving autonomous roadmap. It is maritime focused, but with wider autonomous domains contributing, aimed at achieving the multi-domain integration required of future battlespace systems. Just to look at, on the next slide, multi-domain integration a little further. So maritime autonomy is wider than seaborne assets and include land and air capability. This multi-domain integrated approach will enhance our intelligence, surveillance, target acquisition and reconnaissance capability, ISTAR, or just provide a simple communication barrier, for example, for range extension capabilities. Within maritime, we have significant building blocks to take across the wider domains, from our mission management systems to our ASVs to post-mission analysis capability, or just the given autonomy engine. And cross-domain as well, integration is wider than just the capability itself. It includes reuse of trials, training and support. And these are all key components for cross-domain integration The reuse will deliver not only value for money, but it will reduce the PAN, Defence Line of Development burden, and it's key to embrace a build once, use many approach. So I want to talk about how we are embracing the challenges of autonomy, and within Thales we call it the 3T model. Moving forward with MMCM and wider autonomy, we need to consider three key areas as we look to move towards an autonomous maritime head model. Firstly, technology. Keeping up and baselining products is becoming a significant challenge. No matter how good your obsolescence management and software patching policies are, the acceleration of both hardware and software provides significant challenges when considering the through life aspects of delivering systems. Innovation needs to be addressed wider than technology. We need to look at commercial innovation. It needs to be developed to support the challenges we face in an extremely agile environment. The commercial component and risk tend to drive contracting mechanisms, but we all need to collectively look at how to share risk, service, or product provision and see how we can evolve that to meet the challenge of rapid change. So the next area we're going to look at is trust. We've all read the worldwide headlines regarding Tesla and Uber automation failures in the automotive industry. But in the most recent cases, the autonomous systems hadn't failed and human error was the most likely cause. In the case of Uber, the permissions to test on public roads within the state of Arizona was removed. These cases clearly highlight the legal and ethical challenges we face with emerging human out-of-the-loop technologies. To counter this perception, we need to test and evaluate capabilities to gain wider confidence and develop trust. Through trust, we will be able to deliver the multiple benefits autonomy will bring from achieving objectives quicker and better, reducing costs, and with significantly smaller environmental impact. Embracing wider systems and experience with existing pedigree, particularly in the air domain that meet stringent CAA approval, with significant in-service time will help. And finally, time. As mentioned in the technology area, the rate of change can be driven by a number of factors, but we need the headroom to evolve in a stable manner and a safe manner. Through evolving roadmaps and effective product management, we can stay ahead of the game. The Maritime Autonomy Centre is key to developing the 3Ts and delivering the roadmap to full unmanned systems. The Centre will provide the means to assess and certify, allowing both Thales and our partners to fail fast and therefore succeed fast in a safe and controlled environment. It also provides the ability to rapidly assess emerging technologies. Through the Turnchapel facility, we will develop a dynamic and innovative culture that embraces agility, which will lead to the establishment of a Plymouth-focused, world-leading autonomous centre, with wider marine hubs encompassing wider government, academia, and small to medium enterprises. I'm just going to talk a little bit around the coupling of digital and real world. So to enable our ability to fail fast and therefore succeed fast in a safe and controlled environment, modelling and simulation needs to couple with the real test environment. Digital assurance has been successfully utilised in the wider autonomy space, particularly in the automotive industry. The safety and security of autonomous vehicles is not simply a matter of obstacle avoidance and a lockdown network. They must be seen as elements in a wider context, interacting with the natural environment and the systems in both standard and also fallback operations. Digital will provide opportunity to test a wide range of cases in controlled and safe environments, and we can take various approaches, whether batch testing to gain overall metrics, or if you want to target particular problematic cases utilising Edge. So to summarise, I would like to thank the wider Plymouth and Maritime Autonomous community that I've had the chance to meet or talk with since starting in my new role, who have welcomed me both patiently and supportively as I develop my wider understanding. I look forward to meeting and working with more of you over the coming weeks as my journey in this exciting domain and ecosystem continues. Thank you for listening.
Thank you to David O'Sullivan from Thales. With no human captain or onboard crew, the Mayflower autonomous ship uses the power of AI and automation to traverse the ocean in its quest for data and discovery. Cameras and computer vision systems scan the horizon for hazards. To tell us more, here's Brett Phaneuf, Director of the Mayflower Autonomous Ship Project.
The sea is an awesomely powerful thing. There are vast areas of the ocean that we know literally nothing about. We know more about the surface of the moon than certain parts of our own planet. It's that ignorance that should scare us, because the ocean controls the entire climate on our planet. This project is not about the last 400 years, it's about the next 400, it's about the future. The Mayflower autonomous ship is inspired by the 400th anniversary of the Mayflower crossing from Plymouth to Plymouth.
Well, now we're talking a whole nother story where there's no humans on board. So we've got a ship that's going to make decisions on its own.
It doesn't have anybody sort of in a control room pressing buttons or anything like that.
I did 33.5 years in the Navy. I'd never seen anything like that in my life.
There's no guarantee of success for any number of reasons. It's the beginning of something new.
Have we thought of every possible situation that it could encounter?
Autonomous vessels like the Mayflower will really allow us to collect as much data as possible. What are we going to discover? What does the future hold for this type of research?
The single biggest challenge is the ocean itself. So no ship has ever been built that can survive whatever the ocean could throw at it.
Leveraging technology, autonomy, machine learning and AI is going to open up the door to a new era of ocean science.
The ocean floor is littered with our engineering failures and mistakes. You need to respect the power of what happens out there.
There's still things to be discovered. If we have a zero-risk philosophy, we are doomed.
When we first conceived of this idea, I wasn't sure it was going to be possible. We were talking about an intelligent vehicle out in the middle of the Atlantic Ocean.
We built a ship, put autonomy into it, and now we're learning what that means.
You just maintain your course and speed.
The pressure's certainly building as we're getting closer to the launch. There's a lot that we need to deliver.
Right.
Something going wrong.
What keeps me up at night is we break down somewhere in the middle of the Atlantic, and it's something so trivial.
Working on a boat like this, you kind of have to figure stuff out on your own.
They got some drama. No, we need to find out what happened, but it wasn't responding. So we'd lost comms. I just want to finish shaking her out and start across.
The crossing? The crossing?
The crossing.
So when you say the crossing?
Atlantic.
That little thing?
Yeah.
Yeah, good luck.
When it pulls out of Plymouth and I know it's not coming back for 6 months. When I see the rear end of it and the stern of it going around Ramehead, headed off west, that's going to be exciting.
IBM really likes projects that are really pushing the envelope to do really exciting and novel things.
What if we had hundreds of these vessels? This is going to transform ocean science.
Trying and failing doesn't bother me. It's if we don't do everything we can do to ensure success.
I'm just amazed. I've been seeing computer models floating on beautifully rendered computer water for so many months. To see the real thing is just absolutely mind-blowing. It's the real climax of a number of years, as you say, of work, and yet it's the beginning of a journey. IBM really likes projects that are challenging, so to be involved in projects like this, which are really high profile and really pushing the envelope of what are essentially off-the-shelf technologies on one hand, but bending them out of shape to do really exciting and novel things. That's what most of my career in IBM has been about, and I'm hugely proud to be associated with the Mayflower project. It's just amazing.
One of the things that really excites me about this project is the idea that we're going to be able to actually use some of the technologies that I work with every day to revolutionise the way that we capture data in the ocean.
That's the unique thing about this project. There is no captain. There's no person, actually. It's an AI-based system. So we're calling it the AI captain.
When it pulls out of Plymouth and I know it's not coming back for 6 months. When I see the rear end of it and the stern of it going around Ramehead, headed off west, that's going to be exciting.
IBM really likes projects that are really pushing the envelope to do really exciting and novel things.
What if we had hundreds of these vessels? This is going to transform ocean science.
Trying and failing doesn't bother me. It's if we don't do everything we can do to ensure success.
Thank you to Brett, IBM and all of the Mayflower autonomous ship partners. And later, Matthew Ratzi will give us an update on the progress of the Mayflower project. Now, our final speaker in this part of the Marine Tech Expo is Tom Rooney. Tom is a former Royal Navy weapons engineer. Since leaving the Navy in 2014, he's worked for UK-based subsea technology company Sonadyne. Tom's here to look at communications in the undersea battle space.
The 21st century underwater battle space is a complex arena with its own unique challenges and fast-developing technologies. If we look, for example, at the Royal Navy's vision for the underwater battle space in 2030 and their longer-term vision for 2040, we can see that autonomous and uncrewed robotic systems feature heavily. NATO and other navies have similar visions, in which, as we've heard already this morning, new robotic systems and technologies will be extending the reach of the uncrewed platforms in this demanding domain. A key enabler for underwater operations is communications, particularly in the defence space, where communications need to be both secure and interoperable. Sonadyne are working with the UK Ministry of Defence's Defence Science and Technology Laboratory, DSTL, to develop a new standard for secure waveforms to fully connect the future underwater battle space. In this presentation, I'll discuss the key challenges and requirements for the underwater communication systems, the track record and expertise that Sonadyne have in this area, and provide an overview of the work we're currently doing with DSTL. The underwater battle space will be fought by a wide variety of different assets. Each platform will have their own challenges in terms of size, weight, and power restrictions. They will be manufactured by different companies with different sensors and different mission payloads. The future underwater comms architecture must therefore be platform agnostic and enable these disparate assets to interoperate regardless of the comms hardware suppliers. These advanced platforms will be conducting the full range of underwater warfare roles, including ASW, mine warfare, surveillance and reconnaissance, critical infrastructure defence, and special operations, all needing to operate and cooperate in the most unforgiving of environments. The future comms system must be reliable and adaptable enough to support all of these roles, supporting a wide variety of message content over effective tactical ranges. Speed of light communication systems operating in the surface and air domains deliver very high data speeds. Comparable bandwidths are almost impossible to achieve in the underwater domain, and this is arguably the greatest challenge for delivering effective underwater communications. This image shows the performance comparisons of underwater comms using electromagnetic, optical, and acoustic signals. EM comms are used widely in the above water domain, but also have some niche applications underwater. However, the signal is quickly attenuated, which makes them short range and therefore naturally covert, but they require significant power input in order to be effective. Optical comms arguably provide the highest levels of potential bandwidth and are also naturally covert, especially if ultraviolet wavelengths are used. But the effective range depends on beam width, turbidity, and background light levels. Really, the only effective medium for wide area underwater communications is acoustics. These offer much greater ranges. However, as the signal is transmitted at the speed of sound, propagation latencies are orders of magnitude lower, or higher rather, than radio frequency communications in air, and therefore available bandwidth is greatly reduced. Acoustic signals must also cope with highly variable background noise levels. The waveforms need to be detectable and decodable whilst being transmitted at frequencies and power levels that do not adversely affect the surrounding marine life. In addition, temperature changes in the water column change the speed of sound, and this refracts the path of the acoustic transmissions. Operators in this battle space are familiar with this challenge. They're also familiar with using sonar propagation prediction software. Future AI systems may need to use similar algorithms to autonomously place themselves within effective communication range of other units. By far the most important requirement is security. This is essential for military operations and increasingly desirable for commercial ones. Secure communications are critical to the effective control of the battle space. Assurance of data integrity and confidentiality allows real-time decisions to be made in the battlefield. Therefore, the ability to encrypt and the underwater communications and only demodulate them with the correct cipher key is primary in the requirements list. The existing NATO underwater comm standard, JANUS, was designed as the first interoperable protocol and protocol stack. It provided the first step towards real interoperability. JANUS and other standards, however, do not have the requirements, the capabilities rather, to meet all the requirements of the future underwater battle space, chief amongst them security. Whilst these existing protocol stacks can have security added on, this adds overheads outside of the protocol stack, making it less efficient and effective as a medium. What is needed is a secure by design approach to meet the high demands of the technology entering this battle space. Sonodyne has been leading a technical program to deliver high-integrity, secure waveform for underwater communications set up in response to a DSTL requirement. The work, funded by UK Ministry of Defence via DSTL and primed by Thales UK, seeks to develop FORSIS, an open standard for secure underwater acoustic communications that will enable navies to collaborate and interoperate with assured security. Sonodyne has a long history of success in the field of underwater communications. We developed BlueCom, an industry-leading underwater optical communication system used for high-bandwidth data applications. Its effectiveness was demonstrated when Sky News transmitted live from a submersible 170 meters deep off the Seychelles in March 2019. In the field of acoustics, Sonodyne developed the first commercially available spread spectrum phase-modulated acoustic waveforms for underwater applications. This technology and its successors have revolutionized the subsea engineering in the commercial offshore sectors. Our sixth generation of digital wideband acoustic communications, known as 6G and recently upgraded 6G+, is used extensively in these offshore applications. This common architecture protocol enables multiple coexisting capabilities, including but not restricted to highly precise acoustic positioning, telemetry data comms to UUVs, and data transfer from persistent seabed sensors to surface units. Communications of up to 12.5 kilometers in range and a usable data payload speeds of up to 9 kilobits per second are achievable with this technology. So what is FORSIS? In the words of Alex Hamilton, Principal Communications Scientist at DSTL, it is the development of a high-performance protocol stack that will be available as an unclassified, non-protectively marked standard. It is a secure by design approach using cryptographic keys. DSTL are working with the National Cyber Security Centre to ensure security of these communications is approved to government standards. Adhering to these standards will allow for multi-domain integration across different assets and interoperability between different nations, platforms, and areas within the Navy. The cryptographic keys that Alex mentions will accommodate different levels of interoperability. In the same way that we have UK codes and NATO codes for encrypting above water communications, force commanders will be able to control who has access to the information in the underwater network. There will also be a public code for all users using this unclassified standard. The acoustic waveform, designed jointly by Sonodyne and Newcastle University, underpinning the FORSIS protocol stack, is based on similar spread spectrum modulation technology seen in the highly robust and reliable 6G and 6G+ commercial systems. This new waveform is capable of working across different frequency bands, so to suit the operational requirements and restrictions of each platform and target all environments from confined spaces to deep open waters. The common FORSIS protocol stack, driven by open software-defined modem architecture, also developed by Sonodyne, will provide the appropriate data payload space for the various missions, with the required levels of security through any supported transducer hardware. FORSIS will also enable effective identification of subsea assets as friend or foe, an essential tool for maintaining situational awareness in this increasingly populated battle space. With DSTL, Sonodyne intend to implement this standard and work with third parties to promote its use. Our aim on completing this product will be to offer our customers our trusted and robust commercial off-the-shelf solutions, with the opportunity to utilise the Secure Forces waveform using the same hardware platforms. DSTL have stated that they are looking for vendor buy-in, not vendor lock-in. This will simplify procurement because vendor systems that comply to the standard can be used together, and there's still space for companies to compete. This new marketplace will drive innovation higher up the protocol stack. Rather than focusing on communications, developers can look at application and platform integration, layer processing, autonomy, and graphic user interfaces into the Forces network. So to summarise, Forces is the underwater comms bearer the world has been waiting for. A secure by design, open standard protocol stack, an NCSC approved secure waveform with encryption layers designed in, and an open software-defined modem architecture. Forces will meet the needs of the future underwater battle space and enable greater exploitation of advanced uncrewed and autonomous defence technologies. Thank you for your attention. I look forward to seeing your questions in the Q&A session later.
Thank you to our guest speakers in this session, and I'm delighted to say we have them with us to answer your questions over the next half an hour or so. With me in the studio is David O'Sullivan from Thales, and joining us virtually are Rob Allen and Tom from Sonodyne. Thank you very much, all of you, for joining us. David, here in the studio, I wanted to start with you, first of all, and the developments you took us through there in your presentation. But what have you learned so far in the process that could be used in the wider community? How could it be applied elsewhere?
Yeah, it's an interesting question. I think in general, when you look at actually MMCM operations or MCM operations, when you look at the overarching objectives, there's a planning element, and it's quite significant. You'll be amazed how much detail goes into the planning element of mine countermeasures. We then execute a scenario and missions, and then obviously we evaluate the data and information as well, type thing. Now, those key high-level activities are actually common across lots of maritime operations, and particularly it's very similar in the ASW space, in the anti-submarine warfare space. So the principles of what we do are there. Now, within our capability, I look at it as a toolbox with lots of tools in it. So the autonomous engine, some of the mission management, some of the data management stuff, all of that area is reusable in the wider maritime domains. And also, not just in maritime as well, basically. That's one of the key things here is that when we look across the autonomous space, that when we conduct certain operations, we could be looking at amphibious operations is an interesting one, where potentially we want a mission management system that's going to look after our maritime assets, but also our land assets and air assets in support of those amphibious operations. So as you can see, that one, it's got to be multi-domain integrated, but also it's important that we look at how we can reuse from the technologies that already exist in delivering the next step in maritime autonomy.
Picking up on that theme of wider application, Rob, I've got a question for you on sort of wider application as well. The question is, can your research benefit across other industries such as Formula One?
Yeah, so I think Formula One actually is a really interesting case because it's one of the technologies that we've tried to follow. So I would say, yes, it's directly applicable to Formula One, but I think we're trying to play catch up with them because they're exceptionally far down the line. I think the way that they have such a huge budget for one or two assets gives them quite an ability to be able to produce incredibly accurate digital twins with a huge amount of people, looking at that. So yeah, I think it's directly applicable to something like Formula One. They're probably a little bit further down the line with it than we are, but we're certainly looking right across defence and outside of defence at ways we can apply this technology.
And while we're with you, Robert, another question for you. Do you believe that utilising digital twins will increase maintenance level tasks for on-board crews rather than relying on the original manufacturers and engineers?
I think there's an inevitable change in the way that the assets are maintained on board. However, I think in overall terms, it's likely to decrease the amount of maintenance required. If you take some of the work we're doing on weapon systems, for example, we're able to remove maintenance activities because they were just to sort of verify parts are working as they should do, but we can do that remotely, and our digital twin can understand that whilst the asset's being operated. So I think there's inevitably a change, and I would expect probably a change in skill set potentially for the onboard maintainers, but overall, I think the maintenance burden will reduce significantly.
Tom, a fascinating presentation from you from Sonodyne looking at that underwater comms, and lots of questions have been raised from that. One here for you. Will forces replace JANUS as the NATO underwater comms standard?
I think it's a good question. I think, in short, no. We see JANUS as persisting because that provides the interoperability currently. But the Forces program is a UK sovereign waveform owned by the UK government. We see that sitting alongside JANUS, certainly initially. There's certainly potential for the Forces waveform because of all of its capabilities to potentially become the natural successor for JANUS, or to work with the natural successor for JANUS. We see the JANUS being the kind of the handshake and the interoperability bit to sort of connect to the platforms and assets subsea, but then Forces doing the heavy lifting of moving the data around.
I was fascinated to see in your presentation the challenges presented by simply being underwater in terms of communications, and you alluded to some of the work going on to overcome those challenges. Just take us through what are the principal challenges and how you overcome them, and particularly in the southwest here, there's a lot of awareness of the possible effects of sonar on wildlife and things, and you hinted at that as well. So how do you get that balance where you improve constantly the communications underwater, but you're ensuring minimal impact, if any, on the wildlife that you're sharing that space with?
Really valid points, and it's something that Sonodyne have been working with for the last 50 years or so. We've developed technologies that work effectively in that space, high performance systems that work effectively without harming the environment. It's a multi-challenge piece. That's a big question. The environment itself is the biggest hurdle. The fact that when you're working with radio comms, for example, everything works at the speed of light. You know, that gives you fast communications. It gives you reliable kind of speeds in which to sort of to use for predicting and measuring things. That's not the same underwater. Speed of sound is a multi-variable piece. You know, through the water column, both vertically and horizontally, have changes in the speed of sound. And what that does is that refracts the acoustic signals, so they end up changing. Their path will change on any given day in a different environment. So you have to be able to predict and work out where your communications are going. So you have to put things in place or in range of each other. The ways to overcome that is uses of different frequency ranges. So and the same thing for radio comms. If you want to send radio comms a long way, use a lower frequency because the signals are attenuated less. It's the same thing underwater. So for longer ranges, it's lower frequencies. But then you have to manage the balance between the marine life and the applications, because lower frequencies is where you start getting into the realms of potentially harming or interfering with marine life. So there's a balance to be struck there. So that comes down to the power levels that you transmit as well. Certainly with our commercial systems, we stay out of those harmful frequencies. We were able to establish good long-range or reasonably long-range communications using a higher frequency range that doesn't affect the marine life. And we use waveforms and modulation techniques that give us a far better performance than older traditional technology, if you like. The technology we're talking about with the Forces is using, like I said in my presentation, is using this similar technology based on 6G, our commercial waveform. This uses sort of digital modulation techniques in the same way that digital TV works or your phone works. So it gives you that level of shift in capabilities over frequency modulated systems like our old TV system. So you know so we're able to push the performance envelope whilst still maintaining that safety element in the marine life.
Got more questions for you, Tom, and for you, Rob, but I want to come back to David, who's with me here in the studio. And Dan Cheeseman, rather, earlier was telling us about the challenges of upskilling with this technology rapidly being developed and rapidly being deployed within the Royal Navy. In his case, there was a great need to upskill people and give them the skills to do that. What are the challenges, do you think, for ensuring that people have the knowledge and capability to deliver these systems, maintain them and operate them?
Yeah, no, it is a challenge. It's not just a challenge for the Royal Navy as well, it's a challenge for industry as we embrace new technology. We've had to adapt our processes and also the way we think as engineers as well, and that's as we design these systems. But I think, interestingly, for the Royal Navy specifically, it is going to be quite challenging. You can see, for example, that it's a smaller body of men that are basically going to support the MMCM capability, for example. And on a traditional MCM platform, I would have a marine engineer, a weapon engineer, a comms engineer, and so on. And basically, we've got to start to combine these and look at these, how these roles have got to adapt type thing. Now, that's work the Royal Navy are currently conducting. They're doing a training needs analysis that will recognise the gaps that are going to exist in the skills and knowledge of their personnel. But it is going to be a step change in the same way as we've had to embrace it in industry. The Royal Navy are going to also have to embrace it. I think interesting, going back to some of the points that Dan made, and there was a question regarding recruitment. This technology is cutting edge. It's world leading type thing, and I do actually think that is potentials of attracting a new type of super sailor, as Dan put it, or super soldier type thing, into the Royal Navy, because basically when you look at this is, like we say, it is totally different from what I believe when I joined the Royal Navy back in the 80s, that I would ever see, that it would be an autonomous fleet that we're operating and not actually a physical ship that I'm manning type thing. So it is a step change, and I do think that we will get through it collectively. I think there's certainly lessons to learn from industry that the Royal Navy should look at as well, and it's good to see that they're looking at industrial placements as well, which will help. I think the other interesting part is, particularly for the Plymouth area, so it's encouraging to see Plymouth University now looking, partnering with the Royal Navy as well. And in addition, we know that we've got now autonomy-based apprenticeship schemes, and we're actually looking within Thales to actually put a couple of candidates based in Plymouth onto that scheme to support our Turn Chapel Wharf capability, because, as I said, finding the engineers and adapting them with this skill set is quite a challenge. So I think there's definitely, we've definitely got the skill in the UK, and we've basically got the support to deliver these type of people. It is just a step change, and I think that's what we've got to remember. It's going to be subtly different.
Let me bring Rob in on that point as well. What's happening at Babcock to ensure that you've got the people skills, that the people are coming through with the right level of knowledge to help development further?
Yeah, so we've got a really good grad scheme where we're bringing in really top quality graduates, and once they're in the business, they go and move around our departments and sort of learn a significant amount about it. I think I'd echo the same points, that actually we are starting to find, certainly in my team, in the research and development team, that traditional engineering, we're really pushing it to the limit. So we're looking for people, as well as bringing in graduates and training them, we're also looking mostly for people with PhDs to join us in this sort of work, because it's really pushing the limit of what's achievable.
A couple of other questions for you. One here that says, in your projects, can you support a larger amount and high rate data transfer in a global coverage, e.g. 5G and cellular wireless technologies can provide broadband and high rate data transfer in local regions, while satellite comms provide global coverage?
Yeah, so we can make use of bulk data transfer, but actually one of the things, or the unique challenges I think we have in defence, is that those types of technologies aren't necessarily widely used in all cases. So our system's designed really to work autonomously primarily, so very light touch connection back to us. So we, for instance, in some of the analysis we're doing, our system will turn 3 or 4 gigabytes of data into a few kilobytes and send it back to us. So what it's doing is it's processing the raw data at the point it collects it, generates that understanding, and then just sends a very small packets of data back to us. So whilst we can make use of those technologies, the system's designed really to not need them.
Tom, a question for you, a straightforward one, but a very obvious one. Has Forces been tested in water yet?
Yeah, the program is about 2 years old, so it's been going on for a couple of years, working with DSTL and Newcastle University. It's been tested in open water. We're also running further tests in Plymouth over the summer, and we're looking to demonstrate it at REPMUS exercise in Portugal early in the autumn. So it's an ongoing program. It's still advanced. The waveform works. We have a software modem already sort of developed or prototyped in order to achieve and at least send the signals. And we currently have the software-defined modem being developed for the receive side of things in order to really unlock all the applications that I talked about.
We've seen a little bit already, and we will see as the conference unfolds the role that Plymouth is playing in testing a lot of these systems. How would you sum up the facilities and the knowledge and the technology available in Plymouth to help, in particular, with your project?
Well, Sonodyne has been in Plymouth for a number of years. Although we're a Hampshire company, we have a well-established, long-established training and trials facility here in Plymouth with a couple of vessels as well. But also with our new neighbours, Thales, who we've been working with them as well. They're the primes on this project as well. So, you know, that. With that, and also with the customer being here, you know, with the Royal Navy being present, they're supporting this project as well. So they're keen to see this type of application being used. So Plymouth is kind of the place to be in terms of to demonstrate and to develop this technology further. Like I said, we're doing further tests this summer in the higher level applications of this waveform. So, and it's been happening in Plymouth because of all the facilities that we've already seen this morning.
Well, on that point, let's bring David back in from Thales, because I mean Thales is a massive global company. But what about its presence in Plymouth? How are you working with other businesses based in the city of Plymouth and the marine tech sector here?
So yeah, we've embraced, so within our local ecosystem, so we've embraced a lot of the presenters actually that are presenting today. As Tom rightly says, we're working together on a number of different projects. But again, we work with Babcock closely as well in lots of different areas, particularly in the support domain. And I think what people don't realise is that Thales has been in Plymouth for quite some time now. We've got a significant workforce that's actually based in the dockyard supporting the various submarines and ships, as well as obviously what you've seen grow over the last few years in Turnchapel Wharf. I think it's important for us that we embrace the local companies as well, but I think picking up on the point that Tom makes, Plymouth seems to be the place to be where it comes to autonomous systems. You know, it's attracting the right pedigree of companies that enables us to work in an ecosystem manner. And I think that's probably the important part type thing. It's actually being in the right place for the right technologies.
Let's get Rob's view on this as well. I mean, Babcock is a major employer in the Plymouth area and the wider southwest. How would you sum up Plymouth as a marine technology centre?
So I think you've got all the right people in the right places, which are, you know, following up on what David said. Also, as part of my role, I'm a part-time researcher at Plymouth University in digital twins. So having all of that sort of capability in one hub, and obviously being right next to the ocean, you've got, I think, Europe's largest naval base on your doorstep. As you said, big companies with vast numbers of employees there. It's really the right place to be.
Another question while we've got you there, Rob, for you regarding digital twins. The question is, give us an example of what level of fidelity there is in digital twins. I think that's the summary of the question anyway.
Yeah, so I can't dive into too much detail because most of what we do is on sort of weapon systems and similar, but some of the analysis we're doing now is so sensitive that we're able to predict the torque that a motor should be using down to the point where we can see that it's a few newton meters off where it should be. And we're getting down to our analysis now to the point where we can pinpoint the joint in the system that's sticking just by what we're seeing on the torque results. So our physics models are such high fidelity that they can predict so accurately what we should be seeing that we can really hone in on it. And we've done that successfully now in a few times where we've pinpointed build mistakes, we've pinpointed bad maintenance just through that sort of level of fidelity. So extremely sensitive, good quality physics modeling.
Tom, let me bring you back in because you hinted at one of the other issues, the challenges of communications, but also the challenges of security. And with with more data being transferred across systems, security of that data is paramount. Of course, we're going to talk more about that later in the conference with people who are specifically looking at that. But how much of that is playing into your work in terms of ensuring the data security?
Yeah, it's a huge part of the problem set. It is, and what has kind of is holding back the progression of underwater comms in the past is that security element. You know, that assurance that you can give to the user that they are their information is available only to them, that no one else can intercept it, and especially when you're dealing with military applications. So the DSTL are working with the National Cybersecurity Centre to make sure that the security elements of the forces underwater comms standard meet their requirements, and therefore, if we get their seal of approval, that will hopefully give the customer the assurance that they can use this standard with confidence. It's not just applicable to the military applications either. Increasingly in the commercial domain, our customers want data security as well for their own commercial for reasons. So that's why the forces standard is seen to be an open standard. You know, non-proprietary waveforms owned by the government, but available to all users, so that manufacturers can make equipment that supports it, and then offer their customers, both military and commercial, the assurances of the fact that their data, the information they're sending underwater, is as secure as it can be above water as well.
We saw in your presentation the military applications. Give us a bit more of an idea of some of the wider commercial applications, how it could be used more widely.
Well, again, it's all the same things. It's all the same things that the military are trying to do, but in a different context, if that makes sense. So in terms of ocean science, exploration, and also critical infrastructure. So in terms of renewable energy sources, as well as the oil and gas sector that is still huge and still operating, and also the growing markets and aquaculture and all those sort of things. They're increasingly going to use autonomous, uncrewed underwater systems. They already are. You know, we found that the commercial sector is much more kind of willing to embrace the technology earlier. It was good to see that Dan earlier on was saying that the navies are doing the same things. You know, the MOD is looking at the same thing. They recognise that the commercial sector is already using this technology and getting the most from it. So that's why they're advancing, they're kind of reaching out to the commercial sector in order to gain advantage of that as well, and capitalize on that for military applications. So it's all the same things: underwater uncrewed vehicles that are getting data on, you know, on mapping the ocean's floor, on getting environmental data, science data, so we can better understand our planet and how it all works, and where we sit in it in terms of our sitting on the surface and supporting our environment.
You'll have heard Dan Cheeseman saying earlier on about how very much business focused they're becoming, and how they want their suppliers and the companies they're working with to up the pace to projects in months, not years anymore. How much of a challenge is that going to present to the companies that work with the MOD? What did you think of his business ethos that he's bringing to, or the Royal Navy is bringing to, its procurement procedures?
I think it's exciting and it's encouraging, and we've been working with a few of these organisations for some time now, and the recent developments in their reach out and their agility in getting commercial products into the military domain is encouraging. Where the challenge is the companies like Sonodyne who aren't big enough to be one of the prime contractors. It's how do we fit in amongst that, and how do where do we sit in terms of our kind of commercial assurance, and playing with the bigger fish like Thales, etc., is important in that. So it's like Dan was saying, it's that the MOD want to play. You know, they don't want to put the small and medium-sized enterprises off. They really want to encourage their access, but also to give them the kind of the guarantees that business is successful, that there's more to it than I'm not sure what I'm going to say now.
Well, there was a suggestion from him, wasn't there, that there would be the...
Sure that we don't lose our IP, that we can get our capabilities into those into that realm successfully. Really, that's the challenge.
And there was a suggestion, I guess, that if what you're offering them is good enough, meets what they're requiring, they can even help you negotiate the complex world of finance as well.
Yeah, I think the challenge for us is to make sure that we comply with their systems, as you said this morning, and we're working with that. Definitely.
David, let me bring you back in on this point as well. What did you make of what Dan was saying about this very heavily business-focused approach to procurement and technology? Because technology's developing so rapidly, the whole procurement and development system has to keep pace with that, and that's quite a challenge for companies to match that expectation.
Yeah, no, it is a challenge. It was quite it's a very encouraging comment, and it's glad to see that we're going to see some agility actually in defence procurement. I think for me, what I find is that although we're very good at procuring capability quite quickly, and we've seen change in the behaviours in MOD, and it's been coming through time. But as we've gone to open systems, literally we've been able to deliver software quite rapidly, basically, as long as it's within reason. So that's been around for some years now, as particularly in the combat system space, due to the move to open architecture. I think the wider problem that we've seen in that space is actually the wider defence line of development activities. So it's how you then support these agile procurements and how you train these agile procurements and get the doctrine right, and it's all of the other LODs that tend to suffer with this approach. So as long as we're agile in a manner that we can address all of the DLODs, then I think, I fully support this approach, but it is going to be challenging.
Just sum up for us how big a step change it is, because there will be people familiar with previous procurement processes within the MOD that were slow, that took years, sometimes didn't deliver, went over budget and so on. And what Dan Cheeseman was suggesting earlier on is a very, very different approach. So how much of a step change is this?
It's a drastic change. If I'm going to be, there's got to be commercial innovation with it. It can't just be a case of I'm going to follow an engineering process. So I think the key element is how the commercial innovation adapts to enable us to actually work in an agile manner, and where the risk and how we share risk better as well, I think is going to be a key component to this, of it working properly. Because there's a risk with agile that potentially that we don't actually deliver anything at the end if you get too carried away with the process. So we have got to be careful.
Let me bring Rob in on this as well. I mean, I don't know how much of Dan Cheeseman you heard, but you've obviously got a sense from the conversation we've just had about what the step change he's looking for. What do you make of that very agile approach that the Royal Navy is looking at now?
I think it's incredibly exciting. So my background, I'm a software developer, and working in an agile way is part of our culture. So being able to see that reflected in other industries, in the way we work, in the way our customer works, I think it's incredibly exciting. I think I'd echo some of the previous presenters' points that I think it brings some sort of fairly unique challenges and something, but to be honest, they're quite nice problems to have. And as I said, I think it's incredibly exciting.
Some more questions coming in. I'm keeping an eye on all the questions as they come in from people watching all over the world. One here for you, Tom. Back to Forces. Will Forces be able to integrate with existing command systems?
That's certainly something we're looking at the moment. That's probably a higher level application that will come once Forces is a more mature sort of prospect, i.e. open. Once the open architecture is out there for people to use, they'll be able to develop these ongoing things in terms of applications and different in the physical layer and we're doing the physical layer, but in the network layer and the applications layer, and how this works. Think about it a little bit as kind of your mobile phone network. What we're trying to establish here is an open architecture mobile phone network for underwater. Then people can start developing the apps for that and start to integrate that into existing systems and really take advantage and exploit the capabilities that it offers.
Another question for you, Tom, as well. How much of an issue is power generation in the underwater battle space?
Well, power generation and power consumption, I think, are one of the biggest challenges in the underwater space. Most of these underwater platforms will be running on batteries that will need to be recharged somehow, and rejuvenated. So in order to maximize their mission duration, is getting the most out of that power density that you have in the vehicle. So existing systems that Sonodyne and other companies develop now specifically for UUVs is getting the most out of your power. So making sensors and equipment that runs off as little power as possible whilst delivering the most amount of capability and data. And then, so the underwater communications piece kind of factors into that. Is then there's two parts to this. There's the power consumption and making sure that you can use those communications without draining your power too much, but also in minimizing the amount of time you need to spend sending that communication. So it's working on edge technology to process the data at the edge, on board, on the sensor, on the vehicle, and then send information rather than data through the water column to get the most out of that available bandwidth, which, as you know, is limited underwater, and use the least amount of power as possible on that thing. And it's in the commercial zone. So just one thing, Justin, in the commercial zone, the power generation, there are commercial long duration persistent underwater vehicles being used in the commercial zone that have garages underwater. We see the same thing being applied potentially for the military context as well, where they have power generation and power systems fed into so they can park their UUVs and charge them underwater. And this is certainly something the defence realm is looking at too.
And I wanted to bring David in on the same point, really, because I guess it's appropriate to you as well in mine countermeasures, is the issue of power generation underwater. What sort of challenges does it present you?
Exactly the same as what Tom describes. You know, we're trying to squeeze more and more out of our sensor provisions all the while. They're processor hungry, which is basically asking for more power, which then impacts the endurance of the unmanned vehicle. So it's a balancing act, realistically, because obviously when we start looking at the performance of the sensors or the payloads on the various vehicles, we've got to balance that of the mission objective. And it may be okay to actually reduce the duration because I'm getting so much better performance out of the sensor. But it's a fine line. It's a balancing act that we have to look at every time that we consider this going forward. But technology is accelerating. That's the key thing in all areas. So literally you're processing, you can get far more processing for less power output, and particularly in the GPU space, that it accelerates so quick, driven by the gaming industry, that literally these things, they go to market and you buy one, you can't get it the next week. You've got a new generation out there. So it is positive. In the processor space, it's particularly that the power requirement is reducing quite rapidly all the while. But again, we keep building better and better sensors as well. So we utilise that processing, that's the problem. But we come to a baseline point, and that's the key thing, is we have to get to that baseline point and go back to the mission objective and then do that balancing act over the duration and endurance of the vessel versus the payload and the payload requirements.
And just in our last few minutes, while we're looking ahead, what is the future growth, do you think, for maritime mine countermeasures?
So obviously the UK and French programme continues, so you'll see more activity in the Plymouth area as that programme now moves from phase 1, from the prototype phase, to phase 2, which is a production phase. That's going to continue progressing, but the interest in the capability now is coming in from our various export markets. And it's interesting that the model isn't quite exactly the same. There's some countries that want to embrace full autonomous, but there's also a bit of a move to more of a hybrid model where we're actually keeping men in the loop, but with some autonomy as well. So there's a varying interest, but the key thing is the technology worldwide, the interest, and all you've got to do is look at all the major navies. They are investing heavily in this space. This isn't unique to the Royal Navy. Basically, all navies of any worth are actually investing in this area significantly.
And just while we're looking ahead, let me bring in Rob and Tom at this point. Rob, take us through the next couple of years briefly. What are the sort of key innovations and technologies you're expecting to see happen?
So I'm looking very heavily in, and really exactly the same as David said and Tom touched on, that we're looking at trying to bring in as low power processing as possible, because whilst we don't have power issues necessarily, we want to be able to bring in a lot of edge processing. As Tom said, we want to be sending information rather than data. And as I touched on I think in the first question, that is it. The communications bandwidth is so low that we really, really need to be looking at as much processing power inside our units as possible. So you've got like the rise of the Apple M1 chipset. You've got a bunch of very, very high power in terms of processing power, low power consumption devices, which can give us a huge boost in edge processing. And the further we go with digital twins, the more we understand the edge processing requirements, the more sort of complicated our analysis becomes, the more and more edge processing we need. So we've got our eyes very firmly fixed on that at the moment. We're very sort of closely tied in with NVIDIA, and we're seeing what's going on with those. I think that's our sort of primary thing we're looking at. Secondary is weird and wonderful and new types of sensors that are coming along. So I think, as I said in the presentation, one of the things, the challenges that we have is by taking humans out of the loop, we lose really, really good edge detectors. So there's sat there, humans sat right next to an engine. If it makes a weird noise, if it makes a funny smell, they can pick up on that, but we don't currently have sensors in most cases that can do that. So we're sort of very closely watching for these sort of new generations of sensors that are coming in that might give us the ability to start bridging that gap.
And Tom, while we're looking at future growth, where do you see the next big thing happening in your sector in undersea communications?
Well, I think it's that networking of everything. It's providing this this sort of this open architecture that many systems can operate on, interoperate, and actually form networks and heal networks, etc., underwater. Huge challenge, but we see that the FORCIS waveform with DSTL is going to be the foundation to unlock all of that. And then once that is in place, once that starts to sort of see applications being used, we can see the capability of the underwater battle space and the commercial underwater space as well, sort of rapidly increasing as people apply more capability to it, add their own kind of special capabilities to the mix and applications, etc. And in order to really to give the tools to the people involved, on those more capable platforms, the ability to extend their reach and really understand greater what's happening underwater battle space using these autonomous uncrewed systems.
It's been a brilliant insight into your work, yours as well, Rob, and indeed David. Thank you all of you for joining us today, giving us that insight and some background. Thank you very much for joining us at Marine Tech Expo. And that brings to an end this session. There's a break now for lunch, but when we come back, we'll be touching on some of the issues we've already looked at today, such as cyber security, data protection, and how to ensure the resilience of some of the autonomous vessels we've been talking about. That's coming up after this break.